The Wednesday session on sustainable interfaces. My name is Michael Wesley. I'm a professor at Aarhus University, and it is a great pleasure to me to host this session with 4 absolutely amazing papers. We have today 3 full paper presentations at UIST and also 1 Tokai paper where the authors decided to present it here with us at UIST. And we will directly go to our first presentation. So our first presenter is Luca Lu, or Kuyo Lu, I tried it, and presenting the project Degrade to Function. Let's give Luca a warm welcome.
Thank you. Good morning, everyone. I'm Qiu Yu, also known as Luca from UC Berkeley. And today I'm very excited to present our work, Degrade to Function, towards eco-friendly morphine devices that function through programmed sequential degradation. This work is developed in collaboration with Semina, Mentian, Jihong, Xiao, Yue, Chenyi, and Linian. So this shows the typical lifespan of a device. A lot of research, both within and beyond HCI, has been focusing on unmaking, recycling, and degradable technologies to facilitate waste management, like when the device stops working, which I believe is a very important direction. But if you think about the afterlife phase differently, you will find some mechanism actually operate through degradation. For instance, coals open at the burn, releasing seeds that facilitate restoration after a fire, or consider fuels that blows during the overload to protect the circuit. All these examples inspire us to rethink the afterlife phase and propose that we may leverage degradation for functional purpose, rather than seeing it as simply the end of life. Specifically, in our research, we achieve this by using degradation to trigger transformation for functions. In short, degrade to function. Let me explain this concept with this concrete example, the artificial reef for aquatic habitat restoration. Initially, it will float on the surface after being deployed. Then, as microbes degrade the alginate constraint, the buoyant part will detach after several days, allowing the reef to sink to the seafloor. After another several days, a second set of alginate constraint will break, allowing the reef to unfold and fully establish. It will provide habitat for sea creatures. So how does this example tie back to our concept? As you can see, initially, the functional phase is like more conventional, with no degradation being leveraged. For example, we make it compact to save space during transportation, and the floating ensures that the seeds receive optimal sunlight condition for germination. And since the entire device is made of natural material, it's fully degradable in the end. Beyond that, the degradation of alginate is leveraged to trigger the delayed sinking, allowing the seagrass to root to the seafloor after germination. And further alginate degradation is utilized for delayed unfolding, ensure the reef doesn't expand until the seagrass is firmly anchored to the seafloor. So this basically shows how degradation is naturally integrated and leveraged for the device operation. This is a more detailed diagram of this strategy. I know it can be a little overwhelming. As you can see, there are actually many aspects to consider when you're developing such a device. And in the next part, I will discuss all these design considerations and implementation techniques in detail. So we start by examining the representative environments and extract their primary conditions and understand how those conditions change over time and space. In the reef example, the environment is aquatic, and the primary condition we leverage is the presence of aquatic microbes. Then we identify the types of degradation can be leveraged for different conditions, along with a qualitative understanding of the degradation speed. Like in the reef, biological degradation is used, and it happens over a few days, which essentially matches the life cycle of a seagrass. Sequential transformation is another important part, and we mainly investigated 3 aspects. The first aspect is the responsive component, which undergo accelerated degradation under target conditions, and we defined 3 types: the constraint, such as binding or glue; the carrier, which carries and delivers; and incentive, which induces creatures to consume and digest. And we tested more than 600 samples of 16 materials for their degradation performance under 11 different conditions, based on which we identify suitable materials for each condition, such alginate for aquatic conditions with lots of microbes, mechanism for acidic conditions. And based on this result, we developed this interactive library so everyone can quickly access the bindings and leverage this for designing your own device. As for the artificial reef, it mainly utilizes the constraint made of alginate. The next aspect is the substrate component, which generally degrades much more slowly. This includes actuating structure that store elastic energy for deformation and locomotion, as well as like supplementary structure for protection, motion conversion, and other purpose. Here are some examples of structures and materials that can be leveraged for energy storage, like ranging from simple design to more complex ones, combining like several types of deformation. So the reef mainly consists of bending and buoyancy structures made from wood. The last aspect is sequential control, where we propose 3 fundamental types. For example, the same environmental stimulus can trigger multiple transformation, either in parallel or in series, or different stimuli can trigger different transformation, respectively. And the reef adopts this in-series approach. Lastly, all these dimensions work together to ultimately achieve specific functions. And to determine like what functions are needed, we must first understand the problem we are designing for. The autonomous and degradable nature of our technology inspires us to imagine a bigger picture where all these devices work in different outdoor environments, addressing real-world issues. So here's another application example, acidic soil restoration. You can deploy it in areas at risk of acidic pollution. The maximum constraint will break in hours when the soil becomes acidic, releasing the elastic energy stored in the rubber ring. This will activate the device to rotate and disperse this small pellet. The pellets are made of calcium carbonate and contain beneficial microbes. As they corrode, they neutralize the soil and reintroduce the microbes. This is a device designed for wildfire monitoring. The palm wax, which serves as constraint in this case, will quickly melt when the fire approaches. Then the elastic energy stored in the wooden spring will be released and eject the mini flyer sensors to the air to detect air quality. So the flyers will travel with the strong wind, usually accompany wildfires. Next is the seed pod for feeding and sowing. So after deployment, it will remain outdoors until the weather becomes moist and warm. Then the mold will grow, which decomposes and breaks the agar mixture bonding, causing the entire seed pod to bloom and reveal the seeds inside. The seeds are coated with delicious incentive that attracts the ants to carry them back to their nest. And after the coating is consumed, the seeds are discarded in the nutrition-rich area, nutrition-rich waste area, providing an ideal environment for the seed to take root. Lastly, a device designed to combat desertification. So they are deployed when it is cold, such at night, and their fragile papers made from feather, the small umbrella-shaped thing, made from feather, are bound for protection. Excuse me. And as the temperature rises during the day, the beeswax melts, unbending the wood ribbon, and the papers opens. Now the seed is ready to travel with the wind. When the seed encounters water source, the stalk rapidly dissolves, release the arcane. The arcane is the part, actually the seed is in. Meanwhile, the alginate coating absorbs water and starts to degrade, losing its contents, releasing the fertilizer, helping with anchoring and germination. So that's all about the work, degrade function. Looking forward, we believe this strategy can be potentially applied to devices beyond morphine system, like leveraging degradation to unlock new properties and functions broadly. This has the potential to improve or enhance the system, leading to, something like probably upgrades. Within my research scope, I think this work perfectly demonstrates how I develop innovative technology inspired by nature's power, spanning from actuation, mechanical computation, to energy harnessing, and how I deploy these devices to support human and ecological systems addressing real-world challenges. In addition to this, I explore leveraging generative AI to transform the design process towards AI-aided problem identification, design thinking, and technical implementations. On a related note, I'm on job market this year, looking for a tenure track position. I welcome any opportunities to further discuss my work and explore potential positions. I hope you find this work interesting and inspiring, and I'm ready to take questions. Thank you.
So thank you very much, Luca. Do we